So this is the 12th problem in this series, and the problem number is 1.330. The problem is stating a cylindrical vessel with water is rotated about its vertical axis with a constant angular velocity omega. We need to find the shape of the free surface of water and determine the water pressure distribution over the bottom of the vessel along its radius, provided the pressure at the central point is equal to P naught. So if we approach this problem, let us first of all understand the problem by drawing a necessary diagram. So this is how we can explain the situation which the problem is asking us, that the cylindrical vessel is rotated about vertical axis with omega. So as we approach this problem, we select an elemental mass somewhere here, and before that we select a coordinate system. So over here, to select a coordinate system, we are considering something like this. So we consider this part as x-axis and the rotating axis as y-axis. So over here, if we select an elemental patch of mass dm, then this dm will experience a force in the outward direction dm omega square r, which we are taking this distance as x. So dm omega square x, the weight is in the downward direction, that is equal to dm multiplied by g. So over here, these two forces combined will be pushing this vertical and the horizontal surface, and the net reaction which it receives is in this direction, which we are writing as dn. And over here, if we take a tangent, if we draw a line of tangent like this, where this tangent is at an angle theta, this angle is also theta, then we can say that if we break the component of dn, so we will have two components, one over here, so dn sine theta, and in the upward direction dn cos theta. Then we can say along x-axis, so dn sine theta equals dm omega square x. This is equation number 1 that we have. And along y-axis, we can write dn cos theta equals dmg. So if we divide both the expressions, we get tan theta equals omega square x by g. So if we write tan theta as dy by dx, then we get this as omega square x by g, and on integrating dy equals omega square by g x dx. So as we move a certain distance r, so we can say that y equals omega square x square by 2g. So at any distance x on this axis, that the value is, the increase in height is equal to omega square x square by 2g. So this is the first part of the problem, where it is asking us to find the shape of the free surface of water. So the shape of the free surface of water is a parabola, which is evident from this equation that we have. Now in the second part, it is asking the water pressure distribution over the bottom of the vessel along its radius. So along its radius, that is at a distance r. So if I again select this point, the point which we selected over here, point P, at a distance r, and we have to write pressure over here at the bottom of this vessel, then the pressure at the bottom of this vessel is to be calculated. The central point is having pressure P naught. So this point is having pressure P naught. So at this point P, so pressure at point P is going to be P naught, and an additional pressure will be introduced due to height y. Due to this height y, an additional pressure will be introduced at this point. So at a distance r, the point P is going to experience a pressure P naught, where P naught is the pressure at the center. At the central point the pressure is P naught, it must not be confused with atmospheric pressure, plus rho g, and y over here we are writing it as omega square r square by 2g in terms of r, where r is this distance. So therefore pressure at point P equal P naught plus rho omega square r square by 2. So this is the final part of this problem. This is how we solve this problem, problem number 1.330. It was also the last problem for the fluid mechanics segment.